Okay, we start with a recap. In the previous lecture, we discussed and defined the adjacency matrix of a graph, and then we saw what are subgraphs of a graph. Then we defined the notion of isomorphisms, walks, trails, paths, distance, etc. So these were the main topics that we covered. Now uh, we look at what's called connectedness in graphs. Okay? So when is a graph said to be connected? So a vertex U is said to be connected to a vertex V if you can find a walk from U to V. Okay, so if there is a walk between U and V, then we say U and V are connected in the graph. Now, another way to say this is that the vertex V is reachable from the vertex U. Now, since we are talking about undirected graphs, it is immediate that if there is a reachability, right? If V is reachable from U, then U is also reachable from V, right? So the reachability relation is basically symmetric, right, for undirected graphs. On the other hand, if you were looking at some other types of graphs, which we will come to later, this is not necessarily symmetric. Okay? So we have the reachability relation, and if U and V are reachable, right? V is reachable from U, then we can also say that U is connected to V. Now, if for every pair of the vertices, right? U and V are connected, right? The pairs of vertices are connected. Then we say the graph itself to be connected. So which means that for every pair of vertices, there is a UV walk. Then we say the graph is connected. So if you have a graph where there is a pair of vertices U and V where there is no U to V walk, then the graph is said to be disconnected. If it is not connected, then the graph is disconnected. Now, one can verify that this reachability relation is not just symmetric; it's actually also reflexive and transitive. That is, it's an equivalence relation. Now, if you look at the equivalence relation, then we can talk about the uh, the classes, right? Equivalence classes under this relation, and they will be called the components. Okay? So we will come to that in the next slide, I think. Now, once a graph is connected, right? We know that there is a UV walk, right? But now, if there is a UV walk, one can show that there is also a UV path, right? So therefore, it follows that a graph is connected if and only if G contains a UV path for every pair of vertices in G. So this is another way to define a graph being connected, right? Connectedness of graphs. So what we want to show is like what I would like you to show is that graph these definitions are equivalent. So in fact, we defined earlier graph being connected in another way. So graph is connected if for every partition of the graph into two parts, we said, right, there is an edge which goes across, right? So which has one endpoint in one part and the other endpoint in the other part, right? So these definitions are all meaning that or defining the same thing. So that is another question that you can try to work out as a homework question. Now, the connected components, as I mentioned just before, is the equivalence classes under this reachability relation. Okay. So again, reachability is an equivalence relation is something that you should prove. Now, given a graph, how does these components look like, right? I mean, this is, when you're trying to look at the graph and as a diagram, one can also try to visualize this relation, right? Components. So here is an example, right? You have a graph which is given. The entire thing is a graph. We can even name the vertices if you want, right? 1, 2, 3, 7, 8. Right? So in this graph, if you look at it immediately, you can say which are the graphs, because you can see which of these vertices have walks between them for any pair of vertices, right? For example, if you look at this part, one can verify easily that for any two vertices, there is a walk connecting them, right? Similarly, if you look at this vertex, that vertex itself is alone. I mean, there is no other vertex to which you can find a walk to, right? So therefore, that is by itself a component. And this is also a component, because that is also for any two of them, they are connected to each other in this part. But one should stress that just any subgraph where any two are reachable is not a component, right? For example, let us take this graph itself, right, and look at this part containing the vertices 8, 7, 10, and 11, right? Now this part is of course connected, but it is not a component, right? Because 8 to 7, 7 to 10, 10 to 11, right? 11 to 8, all these are reachable, right? 8 to 10 or 7 to 11. I know there is a walk between any pair of them, but it is not a component, because it is not it is not obtained as an equivalence class under this relation in the graph, right? If you look at the entire graph, the equivalence class is this big part, and the reason is that because of transitivity, right? If 8 to 10 are reachable, and then 10 to 3 is reachable, therefore 8 to 3 or 11 to 10 is reachable, and 10 to 3 is reachable. So 11 to 3 is also reachable, and therefore in the equivalence class, all these vertices will come together, right? And therefore one can also see components as maximal connected subgraphs. Right? So the graph is as a subgraph, it should be connected and a maximal subgraph. So this is another way of defining components, right? So components are maximal connected subgraphs. Now, here is an observation. So if you add an edge with endpoints in different components of a graph, okay, then this combines them to a single component, and which reduces the number of components by exactly one, right? If I just add one edge between two components, right? Because one edge can only have two edges, so you can pick one vertex in one component and other vertex in the other component. And if you put this new edge to this graph, then the graph, these two components join together to become a single component. And why does this become merged to a single component? Because of the transitivity of the reachability relation, right? So because if I pick any two vertices in these two components and connect them, then because of the transitivity of the reachability relation, these two components become a single component. Now, one can ask the following question, that if you delete an edge, right, is it necessary that the number of components increases, right? Or you can say when precisely does the number of components increases? When I delete an edge, right? If I delete an edge, the number of components can change by at most one, right? It cannot increase by more than 1, but it need not always increase. So can you find out when it exactly changes, right, the number? Now a graph, suppose you have a graph on n vertices, right, and suppose it has k edges, then one can show that it has at least n minus k components, right? Using what we just discussed above, one can easily show this. So again, why is this true? You can try to give a proof yourself. So as I mentioned already, whenever you see this y, it is your duty to work out the details and write down in the notes. Okay. Now, we already discussed what are or defined bipartite graphs, right? So a bipartite graph is a graph whose vertex set can be partitioned into two parts, where each edge has one endpoint in one part and the other in the other part. Or in other words, we said that the bipartite graphs are those which can be partitioned into two independent sets. Right? Now, how do you prove this theorem? So this theorem is due to Koenig, and this Koenig has nothing to do with Königsberg. It's the name of a person. And this theorem due to Koenig classifies the bipartite graphs. Okay? So he says that a graph is bipartite if and only if the graph contains no odd cycle. Okay, so this is a very nice characterization, right? You can just look at a graph and see whether it is bipartite or not by checking whether there are odd length cycles, right? Or like if you know that there are no odd length cycles, then you know the graph is bipartite. So this is an if and only if condition. So we need to prove this, both necessity and sufficiency. So first let us see why it is a necessary condition, right? That if the graph is bipartite, then there is no odd cycle. So this is easy to observe because let us look at uh, let us look at what are basically cycles, right? So cycles. So when we defined cycles, paths, etc., we started by defining walks, right? We said that you have walks, and then if the walks is closed, then we have a closed walk. And if the closed walk, the no edge is repeated and it's a closed trail. And if in a trail no vertex is repeated, right? Closed trail, no vertex is repeated, then it is it's a cycle, right? So cycles are basically closed walks, right? Now, given a bipartite graph, let us see why it cannot contain odd cycles, right? So the graph is bipartite, which means that you have two partitions, right? X and Y, and every edge is going from between X and Y, right? Now, suppose there is an odd cycle, which means that there is a closed walk of odd length, right? Because an odd cycle is by definition a odd length walk which is closed, right? And without repeating vertices, right? But since it's an odd cycle, there must be an odd walk for there should be a cycle, right? So now we prove that there cannot be any closed odd walk, right, in the bipartite graph. So why is that? Well, for any closed walk to be there, you have to start from some vertex, right? So let's say take any arbitrary vertex, let's say u. Now from this vertex u, to make a walk, you have to just go through edges, right? So you have to take edges because if it is not 0, then you need at least 1, and then you have to take some edges, right? So if you take an edge, let's say x to some other vertex, I mean u to some other vertex, you know that you are going to switch the sides, right? So you go from the side x to side y. Now for the walk to be closed, you have to come back to u, right? Now coming back to u, you can only do if if you again alternate the side, right? You have to go back to the side y. But now every time I, if I start from the vertices, some vertex in x, then every time I come back to x, right? I take a jump to the side y and then take another jump to the side x, right? So I use two edges to come back to x, and then again, if it is not the vertex u, right? Because we are looking at simple graphs, right? You have to again go to y and then come back, right? If I want to finish a closed walk. So anytime I come back to the side x, I have used an even number of edges. So because I always use even number of edges when I'm on the side x, the closed walk must always be of even length. And since there are no odd length closed walks, there cannot be an odd cycle in the bipartite graph. Okay, so this is the proof. So the proof is simple, right? So let xy be bipartition of G, right? Then every closed walk must cross the bipartition an even number of times, right? And therefore, the graph cannot contain, right, odd cycle, because odd cycles are closed walks, right? So that is the proof of the necessity, right? Now, so since the graph is bipartite, there is a bipartition, and then every closed walk must cross the bipartition an even number of times, right? Uh, and therefore there cannot be an odd cycle because cycles are essentially closed walks. Now, to show the sufficiency, right, we can do the following, right? What we do is that we have to show that we assume that the graph has no odd cycles, right? So let G contain no odd cycles. So we are going to show that the graph is bipartite by actually producing, right, a bipartition. Right? We are going to give a bipartition and say that okay, here is a bipartition. Now for this, we look at a very important and interesting observation, right? We have a very important observation. That is, every closed walk of odd length contains an odd cycle. Okay, so contains a not just a cycle, contains an odd cycle. Okay, so every closed odd walk contains an odd cycle. So why is this true? Well, this is something that you can think and try to show. Maybe there are several ways of proving this, but one easy way to use induction. Okay, so assuming that we have proved this, I will keep it as an exercise also for you. So every closed odd walk contains an odd cycle. Okay, so we are now going to claim the following. Right, suppose u and v, right, suppose I have the graph G and pick some vertex U. Okay, so let U belongs to the vertex set. Now we fix this vertex U. Okay, so we fix the vertex U, and then from U I look at every vertex V and see if there is a UV walk, right? Of course, we can assume without loss of generality that the graph is connected, because if it is not connected, we can work on each component, and if each component is bipartite, then the entire graph is bipartite, right? This is something one can easily show. Again, you can try to see why, right? But this is something one can easily show, right? So suppose I take a connected graph and then pick one vertex. Then for every vertex V in the graph, I see if I can find a UV walk and then look at the parity of this walk. So I pick any walk, let's say W1, and see if W1 is odd length or even length. Now I claim that, let's say that there is a walk W1 of odd length, right? So if W1 is odd length, then let's see if there are any other walks from U to V, right? There could be several walks possible, right? Now, if you pick any walk from U to V, then every such walk must have the same parity, I claim, okay? So, suppose this is not the case, right? And then we have, let's say, another walk, let's say W2 or W3, right? Of, let's say, even parity. Okay? So, if you have two walks from U to V, one is of odd parity and one is of even parity, then I say that the graph must contain an odd cycle. And why do I say this? Because if I have W1 going from U to V is of odd length, and then W2 going from U to V is of even length, then what I do is that I take U to V path W1, and then I traverse in the reverse direction W2 and go from V to U. Okay, so I start from U, take W1 to reach the vertex V, then I take V, then I take W2 and go back to U. Now, what is this walk? So this is a walk, right? Because actually I know like conjunction of walks is also a walk, but this is a closed walk. But now the length of the walk is precisely the number of edges in W1 plus the number of edges in W2, which is an odd number plus an even number, which is an odd walk. So there is a closed walk of odd length, which by our previous observation that every closed road walk must contain an odd cycle, says that there must be an odd cycle in the graph. But this is a contradiction to our assumption that the graph we started with has no odd cycle. So therefore, it must be the case that U and V, every path for any U and V, every UV path must have the same parity. Now, if this is the case, we can define a bipartition easily. Okay, so what I do is that I pick up fix a vertex U, find for every vertex the UV walks, some UV walk, and then find the parity. Right? Now, depending on the parity, I put it into two sets. So all the vertices with even parity goes into set X, and all the vertices with odd parity goes into set Y. And I claim that this is the bipartition of the graph. Okay? So let us see this again. So to prove sufficiency, we start by assumption that the graph is a graph with no cycles of odd length, and we assume without loss of generality G is connected. So again, you have to verify that this assumption can be made. So answer why this is the case. Okay. Now, again, if G has no odd cycle, right, then every UV walk has the same parity, for each vertex v, right? Now, how do we prove this? How did we prove this? That if not, then pick some vertices, let's say u and v, such that we have an even length path, let's say w1, and an odd length path, let's say w2, right? Then w1 plus w2 in reverse order, right, gives a uv closed walk of odd length. And therefore, by our observation, that every closed walk of odd length contains an odd cycle, we get a contradiction, right? Okay, so then since we know that every UV walk has the same parity, right, for any fixed U and any V, we define the partition of the vertex set as follows, right? Each vertex, let's say V in the graph with even length of parity from U, right, goes to the set X, and then those with odd length goes to the set Y. Now, claim is that this X and Y are independent sets. That is, XY is a bipartition, right? So again, to prove this, we assume to the contrary that there is some edge in either X or Y. Right? Let's say that there is an edge X1, X2 in the set X. Now, again, I claim that this contradicts the assumption that there is no odd cycle. So why is that? Because by the definition of X, we defined x1 and x2 to be in the set X because there is a u to x1 walk, right, of even parity, and there is a u to x2 walk of even parity. Now, if I look at the x1 u walk and u to x2 walk, right, that has even plus even, which is even length. But now, if x1, x2 is an edge, then that gives a closed walk of odd length again. So this contains an odd cycle, and which is a contradiction, right? On the other hand, similarly, if you had y, then you know that u to y1 and u to y2 are odd lengths. So odd plus odd is again even, and if y1 y2 is an edge, you again get a closed walk of odd length, and that's it. So therefore, x and y are independent, and therefore xy is a bipartition of the graph. So for each component, one can show that the component is bipartite, and then you can just put together this, right, to get a bipartition of the entire graph. Okay, so we have proved that every bipartite graph, right, contains no odd length cycle, and every graph without any odd length cycle is a bipartite. Okay, now we look at Eulerian graphs. We have defined what are Eulerian graphs earlier, that a graph which admits a closed Eulerian tour is said to be Eulerian. Okay, so here I give two graphs below, and I ask, is one of them Eulerian, or are both of them Eulerian, right? So you can if you try a little bit, you will be able to show that the graph on the left side, right, is actually Eulerian, and the graph on the right side is not Eulerian. And if you spend a little bit of time thinking about this, you should be able to come up with a reason why, and this might lead to an interesting observation that when a graph is going to be Eulerian. Okay. So I want you to think about this for a few minutes before you proceed further. Now, so here is a very nice theorem. The theorem says that a connected graph G admits an Eulerian tour, right? If and only if every vertex of this graph has even degree. Okay? So a connected graph is Eulerian if and only if every vertex has even degree. Now, if you look in the previous page, you will see that, in fact, the graph on the left side, every vertex is of even degree, and the graph on the right side has odd degree for vertices, right? Now, how do you prove this result? Okay, so the claim is that the graph has an Eulerian tour. So if a graph has Eulerian tour, we say the graph is Eulerian. Okay? And if every vertex has even degree, we say the graph is an even graph. These are just simplifications, just to work out the proof. Okay, so now if a graph is Eulerian, then we have to first show that every vertex has even degree, and then we have to show that if a graph has even degree for every vertex, then the graph must also be Eulerian, and the connected graph has this. Okay. Now let us first prove the necessity. In fact, I am going to give the arguments for both with this picture, and then we will try to give a proof and slightly different argument maybe for the sufficiency. So let us see how do we go about proving something like this. Okay. Now first let us assume that so to prove the necessity, right? First let us assume that the graph is Eulerian, which means that there is a closed Eulerian walk. Now, which means I start from some vertex, let's say whichever vertex I want to start from, and then I travel all the edges, right? I travel all the edges, and all the edges I travel exactly once, right? And then come back to the starting vertex, right? Now I claim that uh, you know this means that every vertex has even degree. So why is this? Well, let us look at what happens when I start from a vertex and reach a new vertex. Okay, so every time I enter a vertex, I must leave the vertex, right? Because the tour has to come back to you. So therefore, if I enter a new vertex, then I must also exit it. And therefore the contribution of the this tour, right, the walk, when it enters a vertex and goes out is 2 degrees, right? So this has added 2 to the degree of this. And similarly for this vertex, what happens again, it enters, so eventually it has to exit, right? And if it exits, then I know that again I count 2 to its degree. Now, this is true for every vertex, right? Every internal vertex of this walk, right? Every time I enter a vertex, I also go out of it. So, again, the degree is counted by 2, right? And if it visits again it has to go out, right? Suppose, it visits this again, right? Now, again, it goes out. So, therefore, the contribution here is also 2. So, it increases by 2 every time. Now, this is true for every internal vertex except for the starting vertex, right? Starting vertex we started, and eventually what happens? Eventually, so when we started, it had added only +1, right? But eventually, it has to come back to the starting vertex because we are looking at a closed tour, right? So when it comes back to the vertex for final time, it also contributes a +1 to the degree. So therefore, that is +2 again, right? +1 plus +1. And which means that the contribution of the tour to the degrees of each vertex is going to be a multiple of 2, which is an even number. So therefore, every vertex must have even degree, right? This is clear. Now, the claim is that if a connected graph is even, right? Every vertex has even degree, then it is also Eulerian. So we are going to prove this. We are going to prove this by by the following, right? So we are going to prove this by induction only, number of edges. So we start with a connected graph which is even. Now what I do is that I start from any vertex that I want. Okay, I start from any vertex I want, and then I know that because it's a non-trivial graph. Let's say if it is just single vertex, then it's by itself it's Eulerian, so there is nothing to prove. Otherwise, every vertex of this graph has degree at least 2, right? Then I start from any vertex and take some edge, right? Now because this edge is going to a vertex, and this vertex also has even degree. Once I reach into this vertex, I will be able to go out of this vertex, right? Because it has even degree, so it means that if I use one edge to come in, there is an edge to go out also. So therefore, every time I enter a vertex, I will be able to exit it, because there is no way I will be stuck in a particular vertex, because every time I enter, I know that there is an arc to go out. So I can mark this as use edge, right, with a color, right? And once it is colored, I will not use it again, right? But then again, if I come back to this vertex, then because it is even, I will still have a way to go out, right? So every time I enter, I decrease one edge, but again, because it is even, I can go out of that vertex. So I will be able to go out. So this says that if I start from a vertex u, then the only place where this walk can stop, right? I mean, like can be forced to stop is the vertex where I started from, right? There is no other way I will be able to stop, because every time I enter a vertex, I have an unused edge to go out. So therefore, eventually, it has to end up in the vertex where it started. So I start from a vertex u. Eventually, I will come back to that vertex, right? So there is no other possibility, right? But now the thing is that this may not cover all the edges, right? I mean, I may be able to come back. I may be able to come back to this vertex, but it may not cover all the edges. So now, how do you make sure that we cover all the edges? So once this visit is complete, so I get a tour, right, of this. I get, so this is called such a closed walk, closed trail is called a tour, right? So I get to this closed trail. So what I do, I take this closed trail, and then let me just mark all these edges as use. Now what I look at is that is there any remaining edges which I have not used, right? So if there are remaining edges, we should observe that each of the subgraph that you get, right? There could be several connected subgraphs. Each of these several connected subgraphs are going to be of the same are going to have even degree. So once you have each of these components in the remaining part, we can see that each of them will have even degree for its vertices. and using induction we can cover them, right? But now we have to combine these two to get an Eulerian circuit for the entire graph. So what you do is that you start from your initial vertex, go through this, and then anytime you reach it's a vertex which is incident to a connected, uh, you know, connected component in the graph obtained by removing the first trail, right? Uh, you you do a detour and complete the Eulerian tour in that part first. Come back to this vertex and then continue on the trail. And this you can do every time you reach a vertex which is incident to a component that is not visited so far, right? So and this shows us that we can eventually come back to U, and during this process we cover all the edges. So this is the Eulerian tour that you can get. Okay, so now let us formally prove this. So the lemma, uh, something that we can use is the following: that suppose G is a graph with the minimum degree at least 2, then the graph contains a cycle. So this is a very easy and interesting result, and I want you to try to prove this. So this is why. So this is an observation, let us say, and you can try to prove it yourself. The graph with the minimum degree at least 2 contains a cycle. So we'll use it, and we are going to prove the same, but with a slightly stronger uh, conclusion that you can make. So first we prove the necessity, right? So if G admits an Eulerian circuit, let's say C equal to C1, so V1, V2, etc., V M, comma V1, right? Then every time the trail passes through some vertex, let's say V, it uses two incident edges of V, right? So because if I go from Vi to V and then V to some, Vi plus 1, when Vi plus whatever something, right? Then Vi to V and V to Vi plus 1, right? These two edges have been used, and because it is a trail, we will never use these two edges again, right? So therefore, these two will count 2 to the degree, and then uh, the contribution will be always even. Now for the initial vertex, of course, it is also the final vertex, and the starting edge and the ending edge can be paired together, and this will also count an even number. So therefore, that is the proof of necessity. Every vertex must have even degree. Now assume that we start with a graph which is connected, and we use induction on the number of edges. Let's say m. So the base case is m is equal to 0. If there are no edges and the graph is connected, means that there is a single vertex, right? And this single vertex is by itself an Eulerian tour, right? Because you start from there, no edges there, so I complete all the edges. So that is the closed trail. Now, suppose m is strictly positive, and then since the degrees are even, right? Each vertex has degree at least 2, right? So which means that the graph contains some cycle, right? Because our previous lemma says that if the minimum degree is at least 2, then the graph contains a cycle. So there is some cycle in the graph, right? So we know that there is a cycle in the graph, and we just start with this cycle. So pick up this arbitrary cycle, any cycle that you want, right? So let us say that C is a cycle that you found, and you pick this cycle C, and then we are going to construct our Eulerian tour based on this cycle, just any cycle. So let us take the cycle and consider the graph, right, which is obtained by removing the edges of the cycle C. So G prime is the graph obtained by removing the cycles of cycle edges. Okay, so now every vertex of G prime is also of even degree, right? So this is easy to see, right? So why is this? You can think, right? So the G prime, once you remove edges of C, G prime is also an even graph. Of course, G prime may not be connected, right? Because C may be required to make the graph connected, but it has several components. But now every non-trivial component of G prime also has even degree, and therefore by induction you can say that each of these has Eulerian circuit. Okay, so here is an example to depict this. Right, so you have found this blue cycle. Let's say started with this cycle, and once I remove the cycle C, then you have this several components, right? This is one. Here is another, and here is another, right? Now, once I have this, I can verify that each of the remaining components has all even degrees. And then what do I do? By induction, I can find a Eulerian circuit for each of these, right? So then what do I do? I start from any vertex of C, let's say. I start from any vertex of C, right? And then I check, right? For every vertex in C, when I reach there, I check whether there is any component in G minus C that is incident with this. For example, there is nothing here, so I go forward, right? Now, once I reach here, I see that, okay, there is a component, right, which is incident with this. And therefore, this component, what I do, I will first traverse this component. I will take the short Eulerian tour of this component. And then I will continue to the next vertex. Again, I will see if there is any unused component which is incident. This component is already unvisited component in G minus C which is incident with this. Okay, if it is not, I will continue. Then I see another one. So I finish the tour there. I continue. I finish the tour here, right? And then I continue and then come back to the starting vertex of C. So this will complete all the uh, cycle. So by induction, I each of these smaller components have this circuit, and then so therefore so this is the proof that we traverse C and then we visit any non-trivial component of G dash for the first time. So we take a detour, complete the smaller Eulerian circuit, and continue to the next vertex of C. So once C is completely traversed, we also complete the Eulerian circuit of G. Right? So this is the proof of this. Now, the advantage of this proof is that it also tells you immediately that if you have an Eulerian graph, then the edges of the graph can be decomposed into disjoint cycles, right? So edge disjoint cycle. So this is the corollary, which is called Veblen's theorem. Okay, so Veblen's theorem. So Veblen is a famous topologist, I think. And the Veblen's theorem says that a non-trivial connected graph is Eulerian if and only if it decomposes into pairwise disjoint cycle. So in fact, one can show that this is also an equivalent condition, right? It's an if and only if condition. So the proof follows from the constructive proof that we gave before, right? Okay, so with a few homework questions, let me wind up. So if G is a connected non-trivial graph, then G is Eulerian if and only if every edge of G lies on an odd number of cycles in G. The bipartite graph has a unique bipartition if and only if it is connected. Second question. Third question is that if W is a closed walk of odd lengths, prove that W contains an odd cycle. So this is required for our earlier proof. The graph contains a UV path if and only if it contains a UV walk. Again, I gave this as a question for you. And show that two definitions of graph being connected that we discuss are equivalent, right? What are the ones? One is that there is a partition, and for any partition, you have an edge crossing the partition. And the other one is that for any pair of vertices, there is a UV walk. Right? So that is the homework. Okay, so with this, we wind up for today, and we continue in the next lecture.